And then, are you able to see the screen, the PowerPoint, my screen?
Yes.
Okay. So this is introduction to this exercise, mapping landforms with applications to geomorphology and earthquake geology. And it was designed as an in-class exercise. So when you start to handle it, you might imagine that it's not meant, don't make it more complicated than it is. But because it's designed as an in-class exercise, it also was designed that there would be some amount of instructor sort of feedback during the class. And so you won't maybe get as much of that, but I do want to encourage you to get started early and then ask questions as you go, please. And you know, pencil and paper are totally okay if you can print it out and then just take pictures of the result and turn them in, or use a drawing program, but don't get overly complicated on the methodology. Just make it work well, that's comfortable for you. And then it only has strike slip and reverse fault examples. So I haven't yet built an example of normal faults, but the concepts will be the same. And it's plenty of work. So we had 2 chats. Let me just check. Are we good on any questions? Oh yeah, excellent presentation. And there will be office hours. Okay, so the 2 places, this is in Southern California, the strike slip examples from Wallace Creek area on the San Andreas, and then the reverse faulting cases from Wheeler Ridge, which is part of the transpressional domain adjacent to the San Andreas. So a couple other introductory points. One is about the data. And you know, many of you know this probably pretty well, but a lot of times one of our fundamental data sets is going to be remotely sensed data, either topography or imagery, or one feeding to the other. And so kind of key issue is the resolution of the data. So well, a lot of times we say sort of how many meters per pixel. So regional data are sort of tens to hundreds of meters per pixel. But what we want to do and what we want to use in our work is this local to site scale, where we have decimeter to meter per pixel, or sometimes we say sub-meter representation of features on the ground, either as pixels of elevation, which would be a digital elevation model, or pixels of imagery, something that's photographed from an let's say aircraft or something. And so what we're going to use right now is data that's mostly from airborne laser scanning, and that enables us to make these spectacular topographic data sets at sub-meter resolution. And so just to remind you, a digital elevation model is just every square, which is a pixel, has this constant elevation, and that's the raster. And it's sort of 2.5D, so there's only one elevation per pixel. It doesn't sort of wrap around on itself. And the hillshade is the artificially illuminated digital elevation model, and usually we get those from the northwest. So I probably won't finish all of my intro. I'll make a video to explain some of the details, but this to me is fundamental for our class, is kind of what kind of mapping are we talking about. And this is kind of a classic approach that starts even in the 1960s. And the idea is like you have some sort of piece of topography here with geology, and you can see the 3D block diagram showing that some of the slope breaks and changes are controlled by the geology, which we know. And so we could easily make a geologic map. And all of you are probably quite familiar with geologic maps. But there are other kinds of maps of the same place you could make, like a morphogenetic map. So that's sort of how did the features at the surface develop? Where did they come from? Or a process map, like how does the material transform at the surface? Largely this would be kind of what geomorphic surface processes are operating. Or hydrologic, sort of what's the water doing on the surface and in the near surface. But what we're going to emphasize for this is this morphologic mapping. So it's really simple. It's like a basic language of mapping that's just based on the breaks and changes in topography. And it might sound kind of trivial, but it forces you to look at the topography. That's one of the most important things we know from mapping, is it makes you look at what's there. And once you've looked at it and you use this kind of standard methodology, then you can build more interpretive models, or you can interpret more of what you think is going on. So the first example is from Wallace Creek, and the goal is to have you use large-scale aerial photography, topographic maps to delineate the landforms and identify those famous ones along strike slip faults, and then estimate offsets, interpret simple logs of the excavations, determine the ages of the landforms, and then estimate the slip rate. So you have to make a morphologic and geomorphic map of the site. That's the biggest task. Identify the major landforms, measure the offsets, interpret the trench logs, and compute the slip rate. So here's a image, like a little movie. This is the aerial photography draped over the high resolution topography. And you can, I hope, tell right away there's some fundamental discontinuity in the landscape. And that's the San Andreas Fault. It's been displacing the topography over time. And so the idea of this project is to get you familiar with it. So I'll just zoom ahead. These are just some different views. So the basic idea is to map these breaks using these simple line types. So angular convex break of slope, angular concave break of slope, smoothly convex, etc. And this is from this 1965 paper that kind of laid it out in kind of a classical geographic approach. So here's our language. So this is what you're just going to use to draw. So like if you have a cross section, like a topography with the ridge, you'd put like a little railroad track type of symbol. And then this sort of a slope break would have these patterns, either the teeth or the dashes. And the concave slope break has the teeth sort of touching the inner part of the curve. You can sort of show that it's smoother using some circles. If there's a trough on the slope, you can mark those. So we want to just have a language of graphics that lets us map. And you can feel free to modify, just include them in the explanation. And so here is here's the topography. This is 50 centimeter contour interval. This is what you'll map on. And two key things about this site are these two trenches. And so, but before we get to them, this is just what I mean by the mapping. So don't make it too complicated. So, you know, here is this valley, and there's a basal break and slope, and then we go up to an upper break. So just start off by mapping those breaks everywhere. But also you can map the troughs. You can just use all that language, and I want you to use as many of the graphical words as you can. But then you start to see we abstract. Like once we take a break, the contours, we start to see the line work alone. And then we start to make other basic geomorphic or geologic interpretations, like, okay, this valley floor, you know, that must be the valley floor, and then this must be the fault here. So I really want to emphasize this progressive interpretation from sort of more objective to more interpretive. That's fundamental. But also don't, you know, this sort of shows a level of detail. It doesn't have to be super complicated. So then the trend, this is a key hint. So I want to make sure I get this to you before I stop, is this T5 is cut right here. And it was cut on, there's like the local bedrock, which is 20,000 years old. And then inset into that and deposited is this fluvial material that is a terrace deposit, interpreted as such. And so one thing you'll want to look at is what's the youngest age here. So these are radiocarbon dates, little pieces of charcoal that were found in that deposit. And then in T10, which is up here, the key thing you want to see is C1, C2, C3. So these are fluvial deposits that have paleoflow parallel to the fault, overlain by colluvium, and they're also broken by the fault. And the sedimentary characteristics suggest that the T5 fluvial units correlate with the T10 channel units. And so you want to look again at what's the youngest deposit in this, what's the youngest age in these deposits. So these two relate. And so when you start to reconstruct the landscape, you start to say, well, how does this terrace relate to this channel? You want to look at that. Okay, so that's that. You want to also think about using some scissors when you're done to sort of line things back up. Don't be shy to sort of literally or figuratively cut the topography once you decide where the fault is. So just in maybe, excuse me, for just 1 or 2 more minutes, I'll introduce Wheeler Ridge. So this is now a fold that's uplifting and deforming alluvial fan units in this part of Southern California. So you're going to make a morphologic and geomorphic map of the site, identify the major features. I'm going to give you some ages, and then you're going to compute the uplift and the propagation rate. So this is a famous feature. It's like Wallace Creek. It's world famous. And you can see that there's flow. This Salt Creek flows to the north, and it's been basically progressively blocked and deflected by the uplift of the fold. So here's the digital topography of that site. This data came from one of my former students, Emily Kleber, did a master's on this project and these data. And you see just, you want to start to get a sense of the what was the initial topography like, and then how has it changed. So there's obviously also some significant engineering here. This is the California Aqueduct, basically crossing an active fold. And the reason also that it's there is there's a blind thrust fault underneath. So slip along this blind thrust is uplifting and deforming the topography. So here are some of the key features you want to recognize, and just kind of hints. These are the paleo fan surfaces that are lifted up. And you want to do the same kind of mapping that I just talked about for Wallace Creek, again, to just lay your eye across this landscape and mark what's there. And so Emily used some slightly different symbology, but she was also able to map everything well. The key thing then, so your map on this map, and the key thing was, we're hinting to you, is there are these surfaces, these old fan surfaces that are preserved on the top of this feature, and you can see they get lower as you go to the east, or over here you can see they show the uplift, and you want to use these ages for them over here. So these are thousands of years ago, so just assume those are the correct ages. And then once you measure something like the uplift, you can use the surface age to get the uplift rate. The same thing with the horizontal distance. So we want to look at how this fold has sort of propagated, how it's growing to the east. And so the same thing, distance, age, propagation rate. So I'm going to stop there. I'm sorry to go a couple minutes long. As Chelsea said, there's office hours, ask any questions. We'll have this video for you to refer to, but don't overcomplicate it, but read the text that's there. I tried to embed some hints in the text, and good luck. So thanks. I am going to have to excuse myself. Probably everybody else has to go as well.
Thanks, Ramon.
All right, great, thank you. So this homework assignment is due on Wednesday next week, and we have the office hours on Tuesday. And then, as you guys have been doing, there's another reading assignment on reverse faults that is due on Monday. And then on Tuesday next week, we'll be talking about reverse faults. Are there any final questions?
Where do you post the videos?
They're on the course website. I'll just add the link. So they're on YouTube, and then here on there is our course website with the links to all the videos.
Thank you.
Yes. All right.
Okay, everybody, thanks.
Thank you.
Thank you.
Bye.
Thanks.